while other people are still logging on, let me start with a small introduction. It's my great pleasure to introduce Tan Bui-Thanh from UT Austin. He is professor there since 2013 in the Department of Aerospace Engineering, and Engineering Mechanics. He holds a PhD from MIT, also in aerospace, and a master in high performance computing from Singapore. He is, of course, a specialist on several subjects, including inverse problems, numerical analysis, numerical optimization, all part of things which are, I think, very relevant to this IRTG here. He's associated editor of many journals. He has many awards, which I'm not going to list, but in particular, he got this NSF Career Award, which is quite a huge success. So I'm very happy that he's here today. I'm also very happy that he shared already the notes for all of you to go through and to get at least the basic stuff. Yeah, I wanted to convey to the students here that Tan wants to be or could be interrupted during his talk for questions and and remarks. You can also write to the chat, but you might not be able to see it. But I asked Ella and Ella Steins and Katharina Kilbinger to watch for the chat, and then maybe once there is a message there, they will try to interrupt you, Tan. Also, if you ask a question, would be nice to turn on the video, but yeah, that's it. And regarding the video, I should also say to you as students that this is will be recorded also for you to check later. And finally, I wanted to say that we are very happy that Tan is giving this talk, and he's also on a tight schedule as most of us. And so, in order to catch his plane later, we will cut the break, which was envisioned for 30 minutes. We will cut it short to 10 minutes, just to give him a little more time to reach his plane and not to make him hurry. I think this is fine with all of you. And yeah, without further ado, it's my great pleasure to have you here. Welcome, Tan, and we are looking forward to your presentation. Thanks a lot.
Thanks a lot, Michael. Thanks for attendees. Thanks for coming. So without further ado, let me go directly to the lectures. I hope that many of you, if not all of you, have a look at the material, because it's important. Right? We're going to use at least a large number. I'm going to review it a little bit, but the probability, the crash course in the probability, I hope that you have it either from my note or previously. Okay, so this subject is randomization method for inverse problem, right? That this is our. Can everybody see my writing?
Yes. Yes, okay, we can read.
Perfect. Yeah. For inverse problem and optimization problem. But I'm going to just put the inverse problem here. So why randomization? Right? It requires another lectures. I'm happy to talk to some of you later, but we're gonna actually later. But most of the scalable method nowadays is based on randomization idea, and we're gonna talk a little bit on randomized SVD, right? If some of you have done some kind of data dimensionality reductions, model reductions, you may have heard randomized SVD, one of the perhaps most useful method. But beyond that, right, we have a lot of randomization method that actually very useful. I'm gonna try to cover today. Originally, I wanted to cover the Unifying framework that we developed, but for 3 hours, I think that it's better that we just cover on something that is actually clear and easy for you to follow. And I'm going to ask you to read, either my paper or the other papers for a more complicated problem, right? So I think that is much better than just go into technical stuff, and it's difficult and you don't get much out of it. So we're gonna do something that is manageable, and you hopefully get most out of it, and then more importantly, inspire you to look more into the randomization methods later. Okay, so first, why inverse problem is difficult, right? Let's see why inverse problem why is it so difficult? Just very quick, so that we can put everybody on the same page. So why inverse problem are difficult? I think because you are in the Michael, most of them are in the project, right? Is that right? IRTG, most of the attendees.
Yes.
Okay.
I think, yeah.
So maybe you already understood what inverse problem is, but let me actually remind us, right? So let me actually give you a very simple example. Everybody know how to inverse matrices, but what I'm gonna do is different, right? Let me actually consider this problem. Let me call this is K of X and T, and then it's F of T dt. This is well known, right? This is called, convolution problem. So if you take functional analysis or mathematics before, the convolutions, Fourier transform, these are very closely related. And if you solve the PDEs at the end of the day, you integrate, right? You solve a solution of the PDEs, basically you do integration. So it's most of the problem have a similar form. So the question that we are looking at here, right, is the following: given some data, right, some X G, given G measurement at X as I. This is X, right? Xi for I from 1 ... to n. Let's say example, right? What is, and then also you are given kappa as well. So K, which is the kernel, if you wish, is also given. The question is what is F, Ft, right? So typically the answer, or the straightforward answer, I'm gonna discretize it. So I'm gonna discretize the integral, and with, right, let's say, I don't know, let me just say with m points, right? M points. Or you can think about, this is a Riemann integral, right? You can put, n points on a partition with n points on the interval from between 0 and 1, and then you just approximate using Riemann sum, right? So if you put them together, then you can have some equation like this: G is equal to A F, right, vectors. So F, a vector is unknown, which we don't know, right? F is F1 ... to Fm, and A is a matrix, is belong to R of Nm, right? So it's a very simple problem. Of course, so you can say, okay, how about this? I'm gonna do inverse, right? Inverse problem here. Everybody, this is matrix, right? You can do it. What is the problem here? What is the problem here? I mean, the obvious problem is what? If some of you know, please go ahead. Unless it's even it's trivial question, right? You want to make sure that with me. What is the problem here? If I just solve for alpha, I mean, it was so easy. If you want me to solve inverse problem, this is what I'm going to do. Is there any problem with that? Okay.
And maybe
okay, I have
A1 is very in large dimension, and the A1 inverse is difficult to calculate.
Okay, that's good, of course, right? And that's one of the problem, right? If you know that the inverse of the matrix is n to the cube, right? I mean the qubit time. But one of the problem, of course, the obvious problem is that is n and m is not the same, right? So problems. So what you just said is perfectly correct, but let me add a few more problems, right? And so let me say, I just follow one of the attendees, say Mn could be very large, right? And therefore it's expensive. But this is not actually in a sense, it's a troublesome, right? But troublesome is n could be not equal to m, right? Therefore A is not square, right? So we need to be careful about what we mean by inverse there, right? More importantly, this is a problem. This is a problem here. So called the Hadamard. Hadamard well-posedness. Hadamard's well-posedness. Definition first, right? The problem, let me call this a star. So star or one. So one is well posed. If right, one is well posed. If the following is true, first A is surjective, right? So that means there are at least existence. I mean, you need to make sure that there exist solutions. Otherwise, before you solve any equation, make sure you ask yourself or your advisor, there's any solution or not, right? If there's no solution, then it's a waste of time to do so, right? A is injective. And of course, the best thing is, if the solution is unique. If there are many solutions, then which one is good? That's actually another trouble, right? And actually, the key to the inverse problem is this: A inverse is continuous. Right? We know that the continuous operators are this is also stability. Okay, so A continuous, of course, with respect to G, right? Because G is the data. So A inverse, if it's not continuous, that means a small change in G. Then you have a large change in the solution. That is stability. That's a main problem. So for inverse problem, all of these, most of the for inverse problem in practice. In practice, right? In practice, most right. Hadamard condition, at least one, right? At least one of Hadamard condition actually does not hold. One of the Hadamard conditions does not hold. And especially the third condition, right? Stability conditions. Does not hold. Okay, so that means if you have a small change in the solutions, right? Then no, not the solution, the data, which is the observation. G is the observation. Then you can have a very large change in the solution, which is not what you want, right? This is an ill-posedness, right? And therefore the inverse problem is ill-posed. So inverse problem therefore is ill-posed. Ill-posed. Actually give you a demonstration to make sure to give you, right? So let me actually do the next thing that I'm gonna show you is this to recall SVD, the singular value decomposition. I'm gonna try to convince you singular value decompositions or the SVD, one of the most useful matrix decomposition in out there, right? So what does it say, right? If A is in R and M, and the R is a rank of the matrix, the rank of A, of course, is less than or is equal to the minimum of N M, right? Then M can be, then A can be written as what? Written like this: A is equal to U is a one matrix and sigma, and then V transpose, where sigma is diagonal. Second, U and V are orthonormal. Right? which means that transpose U is identity, V transpose V is identity, right? Orthonormal. The inverse is actually is the transpose. Okay, so there are many other things about SVD, but what I'm going to try to show you is that if we use SVDs, right? If we use this SVD, if we use SVD, right? We have, suppose that you can do the inversion, right? Even not suppose that you can suppose that M is equal to N, then you can do the inverse. Remember that, right? Then F is equal to A inverse G, right? Vectors over there, and therefore this is equal to V sigma inverse U transpose. I'm gonna view the reduced version. Of course, should be like this. So this is U, this is R, right? This is N, this is our U, and then the sigma here R by R, and then this is V transpose, right? V transpose, which is R by M. So we only take the nonce because the rank of the matrix is R. Then of course sigma is invertible, right? It's an R by R matrix. So this is G. Okay, what I'm going to show you next is that a very simple thing here that I can do, right? So this is nothing more than the summation of J from 1 to R. J from 1 to R of what? Of U Uj transpose G divided by sigma, right? Let me say here this, of course, epsilon is equal to diagonal of sigma 1 dot to sigma R. Okay, so this is sigma J, and this is Vj vectors. Let me put a vector here. Okay, so the main point that I'm going to show you is that if I'm going to consider, or in practice, if you do measurement, you're not going to be able to get G exactly, but you actually get something observation. The observation is typically a bit away from the true, right? Because your measurements device anyway has some error. Let me just take a K here, right? Let me take perturbations in the UK direction. Remember that UK is the K columns. Okay, let me actually do here. Uj and Vj are the J columns of the matrix U and V. Okay, so I'm gonna just have a little perturbations in the K directions. Then of course my solution change a little bit, right? F tutor, let me call F tutor is now A inverse of G observed, right? And then if you plug in together, right? Notice that your U is orthonormal. What you get is this. What you get is the summation of Uj. This is a linear algebra, very easy. Everybody trust me. Okay, you just plug it in, and then you expand it out, right? And what you get is the following: the epsilon of UK transpose of G G observed. Let me set here, right? Of the G over to sigma K VK. Okay, so that's what we get, and the key is, if you look at here, right? This is the change between the solution. So therefore you can see that I change the solution F, the true F that you would to get, and the actual thing that you get, a norm here without any saying, right? It's just a Euclidean norm in the usual sense. If you do this, then that becomes an epsilon here, epsilon over sigma K, and the absolute value of UK transpose G, right? Vectors. And then, of course, the norm of the U of the VK is identity. So you see the problem. Okay, so remember, but right, and of course, and the the change in the input, which is G observed minus G, is equal to what? Is equal to epsilon, right? Because so this, right? Of course, this means that G minus G observed is epsilon, right? Because UK is have a unit length. Okay, so you change the input a little bit. This is how much that you change in the output, right? And notice that if sigma k, if sigma k is very small, and this is what typically in practice, right? Because the singular value decays very quickly, most of the application, then F, the change in the solutions is much larger than the change in the input epsilon, or this is G minus G observed. And this is the problem with stability, right? Remember that the Hadamard condition, and that's why this is one of the problem with inverse solution. I'm thinking about if you want to put in some data in your computer, and we know that the computer is actually what at least double machine, right? Of course, most of the machine that you have is double precisions. You can, if you input in some real number, you make error in there, right? And if the error is actually, thinking about sigma case is very, very small, you just a small error by just typing in thing, right? Not because you want it, but for example, if you have a type in the pi, right? Pi is an irrational number. It's impossible for you to have exact pi. So when you put in a computer, there's some error there, right? At least 16 digit, at most 16 digit accuracy. Then if sigma k is more smaller than 10 to the negative 16, then your error is actually very, very large, right? Even though you believe that your input is not that, your error, right? Epsilon is not that large. So that is the key problem in the inverse problem. Okay, so I hope that I convince you the inverse problem is difficult, not because of existence or uniqueness, but also the stability. This is the key, because basically you solve the inverse problem, you get trash, you don't get anything, right? Because the change solution too big that you actually don't even get anything close to the exact solutions. Okay, and this can be a stand to nonlinear problem. And let me actually bypass that like I mentioned before, instead of going to the difficulties. But this is still true for inverse problem. And if you work with the infinite dimensional setting, just a remark here, right? Remark here. You can use the so-called Picard. You can use Picard theorem. This is different than the Picard theorem for ODE, right? Uniqueness solution of the ODE. This is Picard theorem for inverse problem. So Picard problem theorem is a generalizations. If you want, let me know. I can send it to you later. Generalization of SVD in infinite dimensions. So if you work with PDEs, right, or function space, that is, you are in a function in infinite dimensions, and you will say, okay, how about SVD? Does it work anymore? In fact, Picard theorem is a generalization. In fact, I would say the SVD is a simplification of Picard, because Picard theorem was invented, or developed even before SVD, right? So you can use Picard theorem in the infinite dimensional setting. Now, I think that's enough for the introduction to why inverse problem is difficult. Okay, so how to overcome how to overcome the ill-posedness, how to overcome stability. Okay, so what we typically do is we're going to do a regularization, right? Regularizations. So what is regularization? So we're going to put down, okay. So one way to solve, of course, I'm limited ourselves in a very simple setting, right? I'm going to solve the inverse problem in this sense. So I'm going to turn into Y observed. This is observation, which is G, right? Y observed minus a U. U is the inverse solution that we have. So if I don't say anything, that's mean an L2 norm. And for simplicity, typically you also have the noise covariance there, right? But let me ignore on these because that's easy. So you typically can solve, right? You typically can solve the inverse problem by using optimization. You can minimize this, right? But no, we will not be able to go away from the ill-positiveness. One way to overcome ill-positiveness is to use regularizations. So one way to do regularization, or the popular way to do it, is the so-called Tikhonov regularization here, right? And what is Tikhonov regularizations? Tikhonov. I mean, this is how I look at it, right? If you have a perfect parabola, right, then you have a unique solution, right? If you do minimization for the perfect parabola, then you have a unique solution. But because your problem is not perfect parabola, how do you make it unique? So Tikhonov realization is very easy. You can do it, even high school student can think about it, right? I'm just joking here. You just add a parabola, right? This is a parabola here, a perfect parabola. So as soon as that perfect parabola can actually dominate the first term, which is the misfit, then you're good. You have a unique solutions. Okay. So for problem, I just a remark here for nonlinear problem. Everything look the same, but now AU become into G, a function of U, right? G is some so-called forward map. This is the so-called the forward map in the inverse community literatures. Okay, so this is the inverse problem setting that we're gonna do. We have three challenges. We have three challenges. For the first challenge is U is in a very high dimensional space, right? And M is very large, right? Some of us already mentioned about that, very large, and therefore either optimization, which I show above, or Bayesian or statistical methods face the so-called of the curves of dimensionality. Right? Because either you search in high dimensional space to find for a solution, or you do a sampling in a statistical sense in high dimensional, you face the curve dimensionality. And the second problem is a more practical, right? Many of us here doing is that G is typically discretizations, right? Typically solutions, typically a solution process numerical through some numerical discretizations, right? And each, right, where each solution could be very expensive. If you do PD discretization, which is a forward problem, right? You know, each solution could be very expensive. Depends on the mesh, right? Depending on the mesh, depending on the mesh size, the mesh size, you know, implicit or explicit method, and so on and so forth. Okay, and the third problem that we're gonna tackle today, right, is large data. Typically, Y-observed, many applications will be Y-observed, right, which is in N, and N could be very large, right? This is a big data. I'm gonna just put here big data problem, right? There are many applications. Some your application may not have it, right? This is a big data problem. And big data, what is the consequence I/O problem, right? We know that the computer is not computing bound, but memory bound. So the larger the data is, the more problematic that we have to solve. So inverse problem, you see that you have to deal with three challenges at the same time. So this is a forward challenge that you typically do if you solve PDEs. Inverse problem is just have, you know, order of magnitude more difficult, and that's because you have to solve inverse problem many times. So we're gonna So what I'm going to do in this lectures, right? We're going to overcome three, and and two, essentially, and two, using randomizations. But you can do randomization to overcome one as well. But I just want to give you a very easy way to see things, like using the randomization method. So it's kind of sound like a bad idea, right? The problem with deterministic, why should you do randomization method? The reason why randomization method is that because of the following randomizations. For three, and that's what we call, right, the randomized misfits approach for problem 3, right? This what we call is a randomized misfit approach, or RMA. All right. So why randomizations, right? The reasons randomization method is appealing because of a few reasons. The appealing because, and by the way, if you have any question, just stop me, right? I think maybe this is still very elementary, right? We're gonna go into some technicals very soon. Easier in code to understand an algorithm, right? And 2, easy to implement. Easier, typically this is typically true, but I'm gonna put it in code anyway because it may be difficult for the others, right? It is easier to implement, and more importantly, it's typically faster, scalable. It's typically more scalable. And faster. Okay, that's a few reasons. Of course, there's a few books out there, and we can talk more about that. We should have by itself, randomization method should have its own lectures, right? So we're going to bypass that. We're going to go into the real thing. So of background material for you. This is a background material. So for the sake of time, right, we're gonna go a little bit fast for the background material. I hope that you already read the notes that I gave you. So let's say if you want to look at the integral, right, like this, everybody know how to to solve this problem, right? Quadratures or anything that you want to do. How about this question, right? Questions for us is the first question is that how about this I is now, instead of one integral, now I have an integral over domain omega, right, of fx dx, where omega is a subset of Rn, right, and n could be very big. And more importantly, right, the more challenging problem is that how about I want to do integral over the whole Rn? How do you do it? We cannot do quadrature here, right? The interesting, right? Interesting is this. We recall that if you recall, right, for 1D or from A and B here, right, the interval here, if you actually discretize or you put like n intervals, right? This is x0 ... until xn. And this, each of this one is the delta x is equal to b minus a over n, right? Then we know recall for 1D Riemann sum. We know that, right, from an elementary real analysis or even calculus, we know that the summation of f of xi delta x for I from 1 to n, and we know this gonna converge to the integral, right? Everybody know this, a to b. How about this? I'm gonna divide and both sides. I'm gonna divide both sides by 1 over b minus a. Of course, it doesn't change the story, right? I multiply by a scalar. This still converge to 1 over b minus a, integral b a to b f of x dx. Everybody know that too. Now, but using the fact that, right, using the fact that n is equal to what? N is equal to b minus a over delta x, right? We immediately have on the left-hand side is 1 over n summation of f of xi, I from 1 to n. So now we actually see the beauty here, because it says that the average, right? You take the average, it converts to an integral. And if you notice that 1 over b minus a is the density of a uniform distribution u over ab, right? Uniform distributions, then we know that the right hand side is an expectations. So the integral, you can integral or even sum, right, can be understood as the expectation of something, or expectation can be understood as an integral, right? So this is nothing more than expectations, or the mean, if you want to, right, with respect to the uniform, right? And the beauty is this, the beauty is that this is generalized. Any method that you work out there may not be generalized, but this, just a simple Riemann sum, can be generalized to any dimension or infinite domain. This can be generalized, right? Can be generalized to high dimensions, even infinite dimension, right? To high dimensions and unbounded domain. Unbounded or, you know, ugly domain, if you're thinking about that, right? Domain. So, and this is through the so-called laws of large numbers, right? So let me actually remind all of us here about a laws of large number here. Laws of large numbers, LLN. The laws of large numbers says that if you have, right? If you have, we suppose that first MI IID, which is independent identically, right? Identically independent. Are distributed. So IID, random variables. By the way, you know, on the writing, I'm gonna put it in PDF. I'm gonna send my handwriting. I'm not sure whether you're gonna like it anyway, because my handwriting is too ugly. But for the sake, you don't have to compete with me writing. Just listen, right? If you have questions, just let me know. And on the lecture notes, type writing here gonna be sent to you later. Okay, I forgot to mention that. Okay, so they are IID. We assume that the means or the expectations M bar, which is because all of them is the same distribution, right? Expectation of MI, right, is less than infinity. So for I equal to 1 to n. And then the third condition is that the variance. Of course, right, the similar theorem also true for multiple dimensions. Now look at just a scalar. For simplicity to tell you the main message, right? So the first two moments, the mean and variance are finite, then the following is true. If you take the average and if you call Sn is equal to 1 over n summations of mi, I from 1 to n, then Sn converges almost surely. You know, it's just basically, you know, if you took real analysis before, it's almost surely is nothing more than almost everywhere, right? Almost surely. It's the same almost everywhere, but this is in a statistical or probabilistic language, almost surely, or A, E, almost surely to the expectation of M, right? And that's the beauty, because regardless of the expectation or the integral on any domain, but the condition is important, right? The condition is need to be IID. In the example that I show you above, it's just a deterministic thing, right? But in order to generalize, it needs to be IID samples, right? Or draws or distributed with the same distribution. Then you have this. Okay, and in the lecture, in the notes that I send you, there's an application for the large number, right? And this is actually the basics. So large number is the basics, or the backbones, the basic or the backbone of any Monte Carlo method. So if you work with statistical Monte Carlo method, because this method works because of the large numbers, this is significant. It's beyond what we're going to talk today, right? Okay, so look at the notes. I'm going to show you a couple of ways to compute the integrals, but it's not that our main thing here. So we're not going to cover that. So let me see error, mean square error of the large number, or the Monte Carlo methods. Okay, so if you look at the note that I sent you before, then this is actually quite straightforward, right? Now, let us not go into the details. You can read it later. This is a standard results. So you just simply compute. This is the so-on mean square error. You take Sn, which is the average. You minus with the mean, which is supposed to be close, right? These are close to each other. How close? That's basically what you want to do. This is the square of the mean square error. So using the fact that using definitions, using definition of Sn, which is the average, right, and IID, you can get, right, you can get to this. Very simple, trust me. Then you can see it. This is nothing more than sigma square over n. And because this is significant, so we're gonna write it down. We're not gonna use it, but I'm gonna bypassing. I'm gonna do this, right? So that means the mean square error. The mean square error. Check the square root here. Okay, is equal to sigma over square root of n, right? So this is exactly the claim about Monte Carlo method, right? It's converged independent of the dimensions. So Monte Carlo method, converges independent of dimensions. And with respect WRT, with respect to dimensions, right? Because in nowhere there is we see the dimension. N is the number of samples, but the rate is very slow. The rate of 1 over square root n is very slow, right? And then that is a problem with Monte Carlo method. And this is a famous. And you see, if you look at the notes, it's very easy to derive this fundamental result. Okay, so the question for us is not this, right? This is asymptotic, and this is an asymptotic result. This is average, right? And slash asymptotic, of course, you need to take and go to infinity, right? Asymptotic results in order to view it. In practice, right? In practice, this is a question. In practice, you take only one sample, right? In practice, you can take. In practice, we have one set of n samples. Now you cannot take an average when they have samples, MI. What is the error? What is the error? This is no longer mean square error, right? You just look at the particular sample. And this is so-called, in order to tackle this question, this can be answers. This can be answers by A answers, non-asymptotic. Theory. And this is the key behind on the randomized method, why they works, because of the asymptotic, because you only take one sample. How do you know it works? And here we go, right? Non-asymptotic theory. In order to do that, some preparation is needed. So this is non-asymptotic. This is just again is a theory for the laws of large numbers. Okay, we start with this is an easy and standard. I'm not gonna prove it to you. This is the first thing. Is the first lemma is it's so-called markup inequality. So this is a standard. It's very easy to prove. So we're going to bypass that. We're not going to prove it, but which says the following, right? Let M be a non-negative random variable, RV random variables. Then the following holds. What does it hold? The probability, the P probability that M is greater than T. M is greater than T or equal T. For T, any number that is actually positive for on T's, right? It is less than or equal to expectations of M over T. And this is the tail, right? I mean, this is actually not surprising, because if you recall about your real analysis before, right? If a function is integrable, right? What it means that the expectation, right, is finite. If the function is integrable, positive function is integrable, then the tail, right, the mass of the tail must decay, right, to zero, right? At T go to infinity, you see that the right-hand side is going to infinity, right? So the tail of the distribution or the function have a very insignificant mass. Okay, so in other words, right, you see that that converges to zero as T go to infinity. So that's a very easy. But the interesting thing is the next lemma, right? So Chernoff actually upgraded into a very nice manner. It's Chernoff inequality. We're going to use the, okay, so we're not diverging away from the inverse problem, okay? I'm just give you some background, and we get to the inverse problem to solve inverse problem. So bear with me on that. Chernoff inequality has say the following. It turns out, right, if same thing, right, same M is non-negative random variables, then the following is true. Then the probability that M is greater than or equal to, I mean, little m and M is the same, right? For my writing, is less than or equal to what? Expectations of e to the lambda M over to e to the lambda T, right? And this is true for any lambda actually non-zero, and you just minimize, so you minimize the upper bound, right? Lambda is greater than zero, and this is true for on T. And the proof is very easy, so let us just do it using the markup inequality. The key is the probability of M is greater than T, right? E the same as the probability of e to the lambda M greater than or equal to e to the lambda t. Why is that? Because of the ME, the exponential function, is monotonically increasing, right? So these are the same. But then you just simply Markov inequality here, right? Markov here. You see above, right? Markov inequality say that this is the tail. So therefore, it's less than or equal. Less than or equal to the expectation of our random variable, which is e to the lambda m over t, right? T is now e to the lambda t. Everybody see that? And this is true. This is true for, and of course, t need lambda meant to be positive, right? Otherwise, it doesn't work. The monotonically thing does not work, right? Now, then this is always less than the for on lambda. So if it's true for on lambda, then you simply take lambda, you minimize the upper bound, you get the chain of inequality. And that is really, really important. And here's an exercise for you. Exercise for you. And this is the tail of the normal distribution. Tail of the normal distribution. Sorry, I talked too much. Let me check. Everybody is okay? You still can hear me well, right?
Yeah, we can hear you.
Okay, perfect. Okay, I hope this is this is the problem with 3 hours thing, right? 3 hour thing is how much that you can cover, and what is significant, and at the same time what is inspiring enough for the student, right? Without being too fundamental, without being too technical, right? I'm trying to balance these two, so bear with me. All right, so and this is a very important result on the random variables of normal, right? So m, if I assume that m is normally distributed by the normal distribution with mean m bar and sigma square, then you show that, right? Show the following. Show that the expectation. This is nothing that more than just integration, right? You can just do integration by hand. You see, analytically, e to the lambda m is equal to e to the lambda m bar plus lambda square sigma square over 2. This is for on t in R. Very nice, right? For normal distribution, you can actually even integrate that out, right? And then solve, and then using channel to conclude that the probability that m deviate from the means, right? It's mean by t. If you deviate, this is actually, there's a whole literature, right? Whole community on a large deviation, right? Theory, and this is kind of the crash introduction in the large deviation. So basically, you said, okay, what is the probability that my random variable, right, that is t deviated or deviating t unit from my mean? And for normal distribution, you can use chain up above, right? Because I only compute integral for you, or you will, right? E to the t square over 2 sigma square. Very nice, right? Very t greater than 0. So look at this. Not only the chain up inequality tell us that the tail of the distribution decays, right? Polynomially, I mean linearly, and you can think of that way, right? To 0. But Chetnov, right, with the help of Chetnov, he upgraded into exponential, right? And especially for normal distribution, you can see Markov inequality now say that t deviation from the mean is exponentially small. Okay, so that means your random variable very concentrated, and this is also concentration theory, right? Concentration of measure. In other words, let me remark here, right? So m is very concentrated. Around its means, around its mean, right? Okay, so you can ask me, okay, how about m less than m bar, right? This is like t unit, but on a positive side. How about you are not less than, right? How about, actually, let me put that question here. So how about questions? How about the probability? How about a probability that m minus m bar is less than negative t, right? Which is on the other side, on the other side. How about this? How about this? So in order to answer that question, this is one of the most uniform bound, union bound, and we're going to show you the easiest thing that you can ever think about. But it's very useful in this literature, randomization method. You use union bound all the time. It's like if you do math, right? You use Cauchy-Schwarz all the time, right? Union bound is the thing that you use all the time in randomization techniques or community. So what does the union bound say? Let this say the following: let A and B are two random events. And the union bound say that the probability of the union, but therefore the name union bound, right? The union of these two events is less than or is equal to P, the probability of each, the sum of each event, right? Of course, by inductions. You can show that now by induction, and showing that thing is also easy, right? The union I from 1 to n of ai, n event is actually less than or is equal to the summation of the probability of each event I from 1 to n. Okay, the union bound is the most useful thing. Why? Because you can combine, right? Because actually I should say this. I'm sorry. I should say this instead. How about the absolute value, right? Greater than t, because you want to cover both sides, right? That's what I should ask, not the other way around. Okay, so back to our exercise. Back to our exercise, similarly, you can show that the other tail, right, or by symmetry, the other part, you see, less than or equal to negative t is also less than e to the t square. I mean, that's a t square over 2 sigma square. You get the same thing as well. Again, the core t is greater than or equal to 0. Now, by the union bound, right? By the union bound, it's easy to see. Actually, madam, why don't I just do this for you? Before union bound, right? Thus, let me actually conclude this. Thus, using the fact that, right, P of A is equal to the minus P of A prime. Now look at my notes, right? The probability of the event and its complements together, right, is equal to 1. Using this, have that the probability that my m minus m bar, and this is what we care about, right? What is the probability that you make only error, t error, right? From the mean, and this is absolute value. Sorry, it is nothing more than 1 minus the probability, right, that you are t unit away from the mean, right? But P of the event m minus m bar greater than or equal to t is nothing more than the probability of 2 events. The first event is m minus m bar greater than t, right? Union with the m minus m bar less than or is equal to negative t. right? And by the union bound, we know that this is equal to e to the t square over 2 sigma square plus e to the t square minus 2 sigma square, negative here. Okay, so each of the events have the same probability because of the symmetry of the Gaussian distributions. Okay, so in another, what is it? 2, right? 2 of e to the negative t square over 2 sigma square. So in conclusion, therefore, right? Therefore, thus the probability that t unit, I'm making t unit error, right? I'm making t unit error, or I'm t unit deviated away from my means is equal to 1 minus of p. Let me just rewrite this. M bar, right? Greater than t. Now it's less than or equal to 1 No, actually greater. I'm sorry, because the probability, the union bound is less than or equal here, right? So now we have a greater than equal. You notice that this is less than or equal. So minus become is greater than or equal to 1 minus 2 of e minus t square over 2 sigma square. Okay, so this is important results. What does it say? This says that with high probability, you're thinking about as I increase t, right? With very high probability, for, so see, therefore, with high probability, my error, right? This is true. This is true. And what is high? This is 1 minus of 2 exponential of t square over 2 sigma square. I mean, I know some of you doing mathematics, you want to say, oh, okay, man, you always do, infinite precision, right? There's no error, or you can characterize the error. So you said you can ask yourself, or you can ask me right now, what is the point of doing this? I know that this inequality m minus m bar is less than t with high probability, right? I'm t unit, or I make t error from m bar with high probability. You can too, right? You can do, let's say for any t, you can just evaluate that exponential, right? Then you can get that probability. You can ask my question, but then now I'm going to ask you back a question. Now let's say, you can ask yourself whether you're going to go to Aachen, right? RWTA to TH, right? Is that right? RWT, actually the short form of
that's right. That's right. Yeah.
Okay. You can ask yourself, what you can ask yourself. Okay, you can say yourself, if it's no, if it is no, then my probability of going to Aachen, right, RWTH in person is 70%. Let's say, right? Or no, 30%. Actually, 30%. If it's Sunday, I'm gonna go to work. Right, is 70%. Right, that's typically that's only very good. The probability, 70% or 0.7 is going to work. If you are advisor or anybody gonna say, okay, you hear somebody say that 0.7 probability I'm gonna go to work on a Sunday day, and most likely you're gonna go, right? But that is in practice. 0.7 is already as soon as it's over 0.5, most likely you're going to do, right? Of course, unless something that you never want to do. If something that you never want to do is going to be less than that, right? Less than 0.5. So thinking about the practical situation, this is where it's the randomization method or probability theory become important, because in our life, anything 70%, right, of certainty, we're going to do it. Like, let's say you do stock. Next time, next year, Tesla stock going to be increased by two times. And with probability 70%, would you buy stocks? I will do. I'm going to sell my house. I'm going to buy a stock, right? Tesla stock if it's 70% in the next year. Of course, now I'm just joking here, but it just tell you here with high probability is the really important thing, right? Because this can be 0.9 or more than that, depends on t. As you can see, if the larger t is, the smaller the exponential is, and therefore the much higher probability. In practice, this is why randomized method, right? For example, randomized SPD is so powerful because it guarantees you no longer have deterministic bound, right? In mathematics, typically this is what you want to do. Oh, this is my bound. Unfortunately, your bound is no longer deterministic. It's only true with high probability, and that is enough, right? That is enough for practical purposes. Okay, so let's do a little more, and then we have a break. Okay, so that is only for one, right? It's what I just showed you here so far is only one random variables, right? One draw. Remember that the laws of large numbers, the laws of large number, let me go up here. I'm sorry, it's gonna be a little bit easy for you on your side. The laws of large number have the summation of m, right? What do you think? If each of them, we have shown you, I have shown you each of the m, right? Instant of m is close to its mean, right? With high probability. Now, if I take the average, what do you think? Would I get a better probability or larger probability that Sn gonna be close to the mean? What do you think? Let me repeat the question, okay? We have shown M, which is the random realization, and it's just the one random realization, right? And we show with high probability, M is very close to the mean. Now, the laws of large numbers, right, is an average of a number of m, and this is what we do in practice as well, right? Why do we vote, right? Why do we need to vote for the whole country to vote? Because it's a laws of large number there. On average, it's gonna respect what the country says about the candidate, right? Why don't you just pick one random one, right? One random people to vote versus a whole country to vote and take the average, right? Which one actually give you closer to the truth or the mean or the expectation of the whole country? The average over the whole population, or just take one? I think my question is obvious, right? You take the mean, and then that's for us, because it's become an average, because that's what we do, right? Always, take as many people as possible, right? For example, if you want to test the COVID Pfizer, right, or biotech vaccine, what do? You do for a number of people. You cannot do it for one people. Why? Because you do more people, you get better results. But have you ever asked yourself, why doing more people, you get a better result or reflect more about the truth, right? Here we go. I'm gonna show you, take an average is way better, right? To reflect the truth. If you haven't asked that questions, I'm gonna give you, I'm just ask you a question. I'm gonna give you an answer by this right now, right? Now back to the laws of large numbers, right? We ask ourselves, how about this? How about Sn minus m? What's the probability of Sn minus m greater than t, right? How small it is, or of course, right? This event is the complement of the other events. They are complement of each other's. What is it? And I'm going to show you. It's just very simple. Okay, so you need to accept this fact. You need to accept this fact, and it's a very simple fact, right? If mi are normally distributed by mean m and variance sigma square, then Sn is also normally distributed with the mean m bar but the variance is different. The variance is sigma square over n. Okay, then it's still distributed. This is the beauty of the normal distributions. Now you can apply right now. Now channel, or let me go back up here. Okay, here. Where? I'm sorry. Where is it? Okay, here. Star. Remember that in the star we assume that m is a normal distribution, right? With sigma as the variance. So we're gonna apply star now for our new variables, right? So our new variable, which is Sn, okay, actually is right here. It's very nice. They are together here so that you can see. So apply star. Now applying star. Applying stars for Sn, because Sn is normally distributed, right? Then we have the probability, because Sn is a normally distributed. I can use that inequality that I just showed you, m bar, right? And the mean of s bar is Sn is m bar. So less than or equal to t is less than or equal 1 minus e to the negative t squared over 2, right? Sigma squared over n, right? Notice that now sigma squared over n, because this is the variant of the Sn, right? In other words, this is equal to 1 minus 2e to the minus t squared over 2 sigma squared, the usual thing that you see, right? For one instance, now you have n here, and you see, right? You see now the beauty, because as n increases, this is increasing exponentially. Decreases exponentially, right? So more and more people in the vote are testing. You have a higher probability that you make a very small error. See that, right? So therefore, Psn. So for any, so this is for any, if you throw me any t that you want, for any t is greater than 0, the probability of Sn minus m, or how about this? I'm going to make an epsilon to make it usual language, right? For any epsilon delta language, the probability that your epsilon errors is less than or equal. The probability is higher. I'm sorry. Why do I do? I put the wrong inequality, but nobody's tell me. Right? Because it's less than, it doesn't have to, it must be greater than or equal, right? High probability. I know, actually I go fast, I know that. This is e to the negative t squared over 2 sigma squared n, right? So there exists n, so that you can make, right? There exists n, so therefore there exists n such that 1 minus 2 e to the negative t squared over 2 sigma squared and is close to 1, right? So if some event that happened with probability 1, that's the best, right? That's the best, because it's the deterministic event. It's always happen. It's close to the deterministic inequality, right? In other words, for any epsilon greater than 0, there exists an n such that this inequality holds. This inequality holds with a probability, right? Approximately 1. You can take n at large. The larger n is, the closer the probability, and this of course is close to the deterministic inequality, right? So this is the power of having sample over a population instead of 1, right? The more people that you can do experiment with, or the more sample that you have with, the better the results, right? And this is what we do with you in practice all the time. Okay, what I'm gonna do is that I'm gonna stop now, and I let you have a 10-minute break, and we go back what time is it there? Michael?
Sorry, Tan, what time is it?
Yeah, what time is it?
It's now 4:15 p.m. here.
4:15 p.m.
So we
Perfect.
could, meet again at 4:25.
Yeah, about 4:25. Okay, I see you all in a few minutes.
All right.
All right. So that you can digest a little bit, and then I come back. Okay. Can you hear me?
Yeah, we can hear you.
Perfect. Thanks, Ella. Okay. So we do all these work. I'm sorry, it's just a little bit fast, but trust me, it's easy, right? Of course, you can ask me a question after that. Email me, and this is a very fascinating area, and it's I think it's also very beautiful. That's why I wanted to share with you. All right, so I think the next one is coming into closer to what I'm gonna apply for the English problem, right? But just to there, you're gonna see that we're gonna cover the important data, right? Big data, the dimensional reductions, and we're gonna use what we just developed, and then we're gonna use that as a consequence for our English problem. Okay, so this is data reduction data. Dimensionality reductions. Via Johnson, Linden-Strauss. Lemma. And we're gonna derive this lemma so that you can see it and the beauty of it, right? And this is just a very intermediate application, but we're gonna do exactly that application for our English problem. Okay. Now we have looked at the mean. We know the mean that should not deviated away from the average, right? Does not stay away from the mean. It's very close to the mean with high probability, and this is what the driving forces for the random rejections approach, right? So this is a random rejections. This sounds like a crazy idea, right? And why do you want to do random rejection? What do you gain on it? I'm going to show you. Not only you gain, but also you are faster, right? And you are way better. that's the amazing thing about the randomness. I mean, I gave a talk for a very large audience, right? It's just a very informal talk, and actually you can show that the mother nature is very random, right? You never know tomorrow whether it's rainy or sunny or snowy, right? You never know whether you're gonna go to school today. You're not sure either. It's always have some probability there. So everything surrounding our life is uncertain. So it's not surprise, right? It's not surprise that our method should be uncertain as well, random as well, because we want to adapt to the mother nature, right? If the mother nature is random, so are our algorithm. So that's my saying, right? I'm gonna conclude that at the end later. Okay, so random rejection. What is random rejection? So here we go. I'm gonna restrict it to normal distribution only to make them easy, right? But it's also true for the large class. By the way, the exponent can come up. You ask me, oh, what's the point, right? Exponent is only true for the Gaussian. No, it's true for the very large class of random distribution and so-called sub-Gaussian, right? Distribution. And many of the random variable that you can think of, right? Most of the thing that you work out with is actually sub-Gaussian. For example, uniform distribution on the finite interval bounded random variable, they are sub-Gaussian, and these sub-Gaussian random variable have a same property, that is the tail decay exponentially, like we just showed for the Gaussian. So what I show you so far, true assumptions, and that means it's true for many random variable in practice. Okay, so that's what I want you to know. Now I'm gonna continue with our Gaussian's random variable. I'm gonna let A in R and capital N. Right now I have not M but N, capital N, because that stands for the number of samples, right? Remember, we look at the samples where Aij is normally distributed 0 and 1, right? That's very simple thing that you can think of. And we're gonna define, it's not a projection, right? It's not the real projection. I'm gonna define a random projections this way. How does it look like? It looks like this. It looks like this. Z is a new vectors. If you start from X, of course, X is in R N, right? And we define the random projection P as, I take a matrix A divided by the square root of N. And this is X. Okay, so that is the so-called random projection. It's not a projection in the usual sense of the mathematics, right? Because it does not satisfy A squared equal to identity, right? A times A is not identity. Not identity. A squared is not A, so it's not the a real projection operator that we learned from mathematics. But we're going to call this a random projection anyway, because you project, right, a high dimensional space. You can see, right, this is in R N. Oh no, the whole thing. Okay, let's do this. X is in Rn, very capital dimension, right? Z is in Rn. So you move from one space to another. It's just a mapping, right? But we typically call this a random projections. Okay, now exercise for you. Show the following. It's easy, right? We're not going to go through in the class. Show that Zi, right, the components, components Zi of vector Z of Z, right? R, show that these components are IIDs, identically independent distributed random variable RVS with what? With the following: E, expectation of Z, a vector Z, the component. And this is easy, okay? Very easy, just do it and you see it. By linearity, right? Zeros, each component have a mean 0 and variance, and variance, and therefore this is an expectation, this is a variance, right? Actually, when I'm going to do this, the variance of Zi, or the expectation of Zi square, right, is equal to the norm of X. Again, Euclidean norm, standard, right? L2 norm over N. And in particular, the expectations of Z, the output vectors, is the same as the norm of the input vectors. Okay, so that's the beauty, right? Because it's on average, the output have the same length of the input. Okay, so if you think about Hilbert space, preserving length is on matter, right? And you're thinking about, P is some kind of isometry, almost isometry, or it is isometry in average. Okay, so you can see that is the beauty of the random, but you're gonna see more in a second. I'm gonna show you, right? So therefore, on average, P preserve length or distance, right, or distance, and that's all matter for Hilbert space, right? Okay, so but the question is that not, we remember that we don't care about average. Average is easy. How about a particular sample, right? Question: how about a particular, right? A particular. This is again non-asymptotic. A particular realization or P, does it still preserve the distance or not, right? Excuse me. Because this is important. On average, you preserve, and this is another message for you, right? When you show in the lecture notes, and you have seen the same picture and the same message again and again. If you look at the average or expectation, you are close. Then using non-asymptotic theory, which is what we have learned, right? We can show that any random realization that also home with high probability. So that's the key thing. If something hold an average on expectation, then you take a few sample or one sample, it holds, right, with high probability. So that's the key, and that's what we want. That's because in practice you have only one realization or a couple, right? Okay, so to that end, we need, right? The answer is again non-asymptotic, non-asymptotic. And you ask me why do we care about random rejection? As you can see, right, on purpose, I take capital N and N. So this random rejection take you very high dimensional space into a little dimensional space, and yet you still preserve a distance, right? That is beautiful. Even random rejection can do that, right? Non-asymptotic theory or concentration measure, concentrations measure. We have done what we have done is concentrations of measure theory as well, right? Okay, so how do we do it? We actually do exactly what we just did before. We know, so using Chernoff again, using Chernoff inequality. What do you have? The probability that I am Z for a particular Z, that is a little bit from the mean, right? This is the mean. Is epsilon, relatively epsilon from the mean. Is of course equal, I just simply multiply n both sides, right? N Z square, and you're gonna see why we do n later. But up to this point, it's the same, right? You just move things over. You move the x square over to the right hand side. You multiply by n, and this is monotonically invertible, and therefore the probability is the same. But then Chernoff says that the right hand side or the last thing is less than or equal to what? Chernoff is less than or equal to the expectations, right? The expectations of the of what? Of n Z square, right? Over to E. No, actually that's a lambda, right? We multiply lambda. Remember that we're going to take the minimization of the lambda greater than T, and this is greater than over exponential of lambda of n times 1 plus epsilon x. This is a Chernoff inequality, right? Which is a variance of the Markov inequality. Okay, so that Chernoff, nothing more difficult, right? Multiply by n upon lambda. Lambda is greater than 0. Now this is the typical thing that we do, right? In this business, you do Chernoff and then you use the IID assumption on ZI. Actually, we just prove in the exercise, right? IID of ZI in the exercise that I asked you to do. If it's IID which is independent, then the expectation, right? The expectation. Oh, I'm sorry, I have an exponential here. Sorry, I missed the exponential here. Exponential of n lambda n Z square, right? Notice that e to the lambda n Z square is nothing more than what? Nothing more than the e to the lambda n summation of ZI square, right? I from 1 to little n, right? That's what we have, and well, we know that if it's IID independent, I mean, if you, again, it's my note again, please, then this IID, then this is nothing more than the product of the expectation. The expectations of the product is the product of the expectations, which is E because of the IID. And this is the same thing that we do. You see the techniques, right? ZI square. I from 1 to n. Any questions up to this point? I should move this a little bit here. Okay, let me rewrite this a little bit to make it a little bit clearer. This is ZI square. Okay, so if I use this, I immediately have, oh, this is nothing more than the minimizations of lambda greater than t. I'm going to move the denominator into the numerator to look, you know, I don't have to write the denominator again. It's same thing, right? Just move the denominator into the numerator and I just rewrite. So this step is slow. So what we need to do is to compute the expectation. And in fact, this is called a moment generating function, but I think we just need to write this out. Therefore, we need to estimate the moment generating function. I didn't console, I should have done so. Moment generating functions. We need to estimate this. E to the lambda and zi square. And 1 is enough because all of zi are the same, right? They're same distributed in the exercise that I show you. Okay, but in order to do that, then I ask you another exercise here. Exercise, suppose, and when I say exercise, it's very easy, okay? It's just that we don't have time to go over it, but it's an integration business here. If C is normally distributed, right, with 0 mean and variance sigma square, and I suppose that T is less than or equal to 1 over 2 sigma square, right? Show that the expectations of e to the t c square is equal. You should take the integral, should evaluate it integral, and this is a Gaussian integral, is square root of C1 a square root of 1 minus 2t sigma square, right? And notice that the condition for t is needed for the square root to make sense, right? Then conclude. If you do that, right, this is very simple integration by normal distribution, right? Hence, maybe they'll do hint here. Hence, using the fact that the integral 1 over square root of 2 pi of e to the negative of theta square over 2, negative infinity to infinity, d theta is equal to 1, right? You just use this fact. Then it's important that we have this, because this is what we need, e to the lambda n zi square, right? Is then you can just apply to e to the lambda n zi square. What you get is very similar, right? What you get is become now 1 minus. So you can estimate very nicely for the normal distributions, then for lambda less than or equal to 1 over 2 of the norm of x squared. Okay, so then show that, then deduce. It's easy, right? If you can do the first one, then you can deduce this. The first one is in turn is also easy by integration. So please do so. Please do so. Now, so okay. So then we can rewrite our problem here. Remember that we start from this. This, right, is less than or equal to this. So I'm going to rewrite that. I'm going to rewrite This one, I'm going to copy this over. I'll copy. I'm going to paste here. And this is less than, and using the SSI, right? This is going to be less than or equal to the minimum for lambda greater than 0. And of course, in this case, now you need to be limited, right? Lambda have two conditions: greater than or equal to 0, less than or equal to 1 over 2 of x squared of what? Of n over 2 f of lambda. Where you just do substitution in there, right? Where if you do substitutions, so trust me, then you have f of lambda is equal to -2 lambda 1 plus epsilon x squared minus log, natural log of 1 minus 2 lambda x squared. Okay, so do substitution, and the right hand side can be written by f, and it's very insert symbol, right? Then where f at 10 is minimum, so you just do take the derivative minimum, symbol business, right? Taking the derivative, set the derivative to 0, and check for the minimum. Then at 10 is minimum at x lambda star is equal to epsilon over 2 1 plus epsilon x squared. Okay, thus we have, right? Then you do substitution inside, right? Then you just simply and thus, and using the fact, and using the fact, and this is weird, right? This is a technical thing that is simple inequality, but how do you know, right? That's a different story. You can do, you can check on this because we know the epsilon is small. So this is inequality is only true. Check that are 2 for all epsilon between 0 and 1. Using the fact that using this inequality with, maybe you never use it, but now you can do it. It's just a simple Taylor expansion, right? You can show that. And using this fact, we have what? We have the probability. We have the probability. Back to our business here, right? Z squared greater than 1 plus epsilon x squared is less than or equal to e to the n over 2 of n over 2 of negative epsilon squared over 2 plus epsilon to the cube over 3. Very nice, very nice. Okay. Now, using the same, you see that you again exponential decays. Remember that epsilon is small, so the quadratic term dominate, right? So negative e to the power negative to e to the power negative. What we want to choose epsilon small because we want to know small deviation from the mean, which is x squared, right? Of z. All right. So you get a similar behavior, exponential decays to 0, and as a function of n here, you see this is the beauty here because n is here. The larger n is, the faster the decays. Same story. Exercise using the same philosophy, right? Similarly show that or identically similarly show that. So what? So this show that the probability that z squared less than or is equal to 1 minus epsilon x squared is less than or equal to e, right? E to the power n to over 2, same thing. Epsilon the cube to 3. So you get the same inequality. And now, as you can see, How do I combine these two inequality in the box? Can somebody tell me? What should I use? I need your answer. Oh, you completely lost. Oh, I already lost you. I'm doing too fast.
I think,
How do
sorry,
I?
Tan, can you hear me?
Yes.
I think you need to sum the two probabilities like we did before, right?
Yeah, what was the name for that? So now the probability, so I have these two inequality, right? Let me actually write down here. Z square is less than or equal to 1 plus epsilon, okay, or, okay, actually. The probability that Z square is greater than 1 plus epsilon x square, or Z square less than or equal to 1 minus epsilon x square. What should I do? I want to do this. I want to understand this, right? Because, go ahead. Go ahead, somebody say something.
Sorry, Tan. So the probability of both before we had the union bound. So I think it's the same here, right?
Yeah, very good. The union bound again, right? So this by union bound, remember that Cauchy-Schwarz, or this is union bound, is the Cauchy-Schwarz in the concentration of measure, unison bound. Very simple, right? Union bound. You immediately see that this is less than or equal to 2 of e to the n over 2 of minus epsilon square over 2 plus epsilon square cubed 2 over 3. Okay, and therefore the probability of you are in between, right? This is you are on the other two sides. Now you are in between, or you make only epsilon error, right? Relatively distant error in the size. 1 minus epsilon x square. Okay, so is equal greater than equal to 1 minus, right? Same technique. Union bound, and then the fact that the probability of A is equal to 1 minus probability of A prime, the complements. Same technique, nothing difficult. It's just, I know it's a little bit fast, but trust me, it's not difficult at all. Just use the note PA is equal to 1 minus PA prime, or complements. And this is the beauty, right? This is the beauty because it says that the error that you make in distance, epsilon error that you make, right, is almost isometry here. You can see, right, with is very small with high probability. Not worse, right? Not worse. This is the same as saying. This is the same as saying that Z square is less than or equal to 1 x square greater than 1 minus epsilon x square. This is true, holds with very high probability, right? With very high probability. And what probability? 1 minus 2e to the n over 2 square epsilon square over 2 plus epsilon to the cube over 3. With high probability, right? As n increases, right? Exponentially. Good. All right. So this is for one pair, right? Or one projections. So typically you have a lot of, this is on the classification, right? I think this is in practical situation where you don't have one point that you project, right? X, you don't have only one X you project. If you have only one, this results holds. How about if you have many of them, many of X, then you projections. Will you still have this, right? Questions. M, right? Vectors. M vectors. X. I'm going to use this superscript, right? Xi. J from 1 ... to M. right? You have m vectors. Then what is the probability that zi, right, which is equal to p, remember the projection on xi, but the probability that zi is epsilon away from xi, right? For all, this is important, for all m. And amazingly, we're going to use Newton bound again, okay, for all m. We want the, you cannot simply conclude here, oh, this is true for one vector and it's true for all vector. That's inaccurate statement, right? So you have to use Newton bound in order to talk about n vectors. And how do you do it? It's very easy. Newton bound. We have first, right? First we look at for the worst case scenario, the probability that some pair has epsilon distortion, right? And this is, right, by mathematics, you know, it's a set theory. This is nothing more than the probability of union of pair I, right? Pair I has epsilon distortions. I from 1 to m. Everybody okay with me on this? This equality, some pair has epsilon distortion is the same. The probability is the same as saying that the union of at least one pair has the epsilon distortion, basically, right? If some pair has a epsilon distortion, then that's this one. And that's at least one is a union, right? A union that of the event that pair I has epsilon distribution distortions. Everybody okay with me on this? Because that's the only key. That's the only thing that we need, right? Now you can use union bound. Union bound. When union bound, this is nothing more than the probability, right? The summations. The summation I from 1 to m of the probability that pair I has epsilon distortion, right? And we already show above. We already show above that the probability of pair I has epsilon distortions is less than is equal to what? Up there, right? That is equal less than equal to 1 minus 2. No, actually, no, up here, not 1 minus 2. Okay, less than this here. This is oh, this is the one. Actually, this is the one. Okay, this is the one. Let me box this for you. This is the one, right? This is one pair have epsilon distortions. Okay, let me call this is a star. This is one pair, right? One x and z. That's one pair. Have epsilon distortion. You are epsilon away from your mean with x squared. Is less than or equal to not 1 minus 2 e to the n over 2 epsilon over 2 plus epsilon over 3 epsilon to the cube over 3. Okay, one pair is like that. Now we have n pair, right? All the pair are the same, right? And because they are IID. Therefore, each of them are the same. Each of them is less than 2 to the exponential. Then m of them you just have m, right? Together, so you have 2m of exponential n over 2 of negative epsilon square over 2 plus epsilon cube over 3. Everybody see that? Okay, so now if we want now, if we want that the probability that some pair has epsilon distortions, less than or equal to 1 over m to the beta. We want to make this small, right? On purpose, you see that 1 over m to the beta. What is beta? Okay, so we simply set, we can find beta by simply setting the actually, I'm sorry, how many pair? I'm sorry, this is not true. If you have m, if you have m vectors, how many pairs total? I'm sorry, that actually I say m pairs incorrect. How many possible pair? Because you want, you know, remember that of course each, this is not the pair. Okay. So my apology. Okay, it's not the pair of okay, so then we have, and actually that, let me actually, I forgot to mention that there, and there are m minus 1, right, pair over 2 pairs of zijj, right, because you want to keep the relative distance between the input vectors. Right? If you have m input vectors, you have m times m minus 1 over 2 pair, right? And you want to keep the distance between these two, the projection. You want to be design a projection such that the relative distance between these pairs holds with high probabilities. So you have actually m times m minus 1 over 2 pairs of zijj. My apologies. Okay, so this, you have m minus 1 over 2 pairs. This is m minus 1 over 2 pair. So this would be now m minus 1, right? The 2 cancel out. So then if you want the probability that some pair has a epsilon distortion very small, in particular less than m to the power beta, then you simply set this, right? Because we know that the probability of some pair is less than or is equal to this. Less than or is equal to 1 over m to the power beta, right? And this implies that the number, right, the dimensions that you do projection. This is, remember that n is the number of rows of the random matrix, right? So the number of rows of random matrix must be greater or equal to beta. And this is a practical issue, right? Log of m plus 2 of log of m times m minus 1 over epsilon square over 2 epsilon the cube over 3. Okay, so I haven't tell you how to determine, right, n, and this is, here we go, we have determined n based on the probability that we decide. So we have shown, we have proved, so we have proved or derived the following theorem, the Scholl lemma, right? Johnson's Lindenstrauss lemma. Johnson, Lindenstrauss. What does it say? It say the following. We just did it. Consider m vectors x, I, in n, capital N, right? I from 1 to ... to m, where n is very large, right? This is a high dimensional data, very high dimensional data, and we define. Remember that we define P is equal to A over square root of n, right? As a matrix in n little n capital N, where Aij is normally distributed standard. Then for any beta greater than 0, if we choose the embedding space dimension, you see that we have embed R capital N into R little m, right? Embedding dimensions. If we choose embedding that dimensions and satisfying 2 star here, satisfying 2 star, then with the probability at least what? At least 1 minus m to the power of negative beta. Okay, so with high probability, we have the projection, right, of x I pair, ij pair, minus p of xj. This is the embedding, right? After you project, this is the embedding compared to the original distance between xi and xj. You make only epsilon error with very high probability, right? And this is the key of data deductions. Okay, so we have shown that there exists, and in fact, it's a random projections. And this is just a version of Johnson-Lindner-Strauss lemma, right? So you can embed high dimensional space into a small dimensional space, and yet we still preserve the distance with high probability. And that is the key. Okay. And this is a corollary. We are now ready for our inverse problem. Okay, corollary. You know, we're not going to prove this, but because it's require a net, epsilon net. If you remember, if you took real analysis, right, there's an when you prove compactness of a set, you use typically your epsilon covering, right, a covering of a compact set, open cover and subcover, right? So we have to need to invoke that thing in order to prove this. In order, right? But the key is the Johnson-Lindner-Strauss that we just did. So the corollary is not quite corollary because it's require additional thing, which we assume that you know, right? So if you let m, or let m I distribute by the normal 0 identity. Okay, this is a vectors. These are normal distributions. Then for any epsilon greater than 0, they're homes. They hold that the P and P transpose. No, P transpose P minus I. Right. This is close to identity with probability. At least 1 over 1 minus 2 exponentials with a probability at least C, right? And actually this is yeah, actually let's say P. Remember P is R and N, right? So with the probability C N to the epsilon square, right? And this is very, very nice because again, N as N increases, you have a higher probabilities. And where C where C is an absolute constant that does not depend on anything. It's a constant, and that's a beauty of using linear structure, or what we just show. What we just show, you can use a little bit of extension from compactness to show this thing, right? Because we know that on expectations, we know that expectations of P transpose P is identity. And this shows that, okay, with N, capital N samples, you are very close to the identity with high probability, right? Same story, same thing. Now we are ready for our inverse problem. Now back to our inverse problem. I'm gonna use this. We're gonna use thing that we have just developed, right? To do thing back to our inverse problem. How do we actually gonna use this, right? It doesn't seem to be related at all. Okay, so recall that, recall that we need to minimize the y observed vectors minus a u, right, square, plus u minus u0 square, alpha over 2, 1 over 2. Right, this is the deterministic inverse problem, right? You can extend it to statistical as well. Okay, so we look at this is the so-called the misfit, right? This is the misfit, and this is the regularization term. Okay, so notice the misfit. Notice that the misfit. Notice that the misfit is equal to 1/2 of y observed. I mean, this is a trivial fact, right? Transpose times y observed. Everybody okay with me on that? This is the definition of the L2 norm, right? Now you see where we think why I'm going to do something weird, and notice that, right? I have an identity here. Identity doesn't do anything, right? But the key thing is that if I assume that my R is a random variables whose expectation is a random variable, I assume, and there are many of them, a random variable such that the expectation R transpose is equal to identity, I assume, right? There's many of them. Gaussian distribution, Rademacher distributions, a lot of them, right? That have this property. Then this is equal to 1/2 of y observed minus AU transpose expectations of R transpose y observed minus AU. Everybody see that? Let's see whether you were still there. Hopefully, right? I just didn't do anything but just replace identity with the expectation of R minus R squared. And now I'm going to use the linearity of expectation. What do we do? If I do linearity of expectations, what I get is expectations of 1/2 of y observed minus AU transpose R, right? R transpose of y observed minus AU, right? And notice that R is in what? R is in Rn, right? R is in Rn. All right. So now the next thing I do, very, very large number, Monte Carlo, or large number, Monte Carlo, that we just did before. Or law of large numbers, right? So we're going to approximate this. We know, right? We know that the law approximate. This is the approximate sign, okay? Vertical approximate sign. This is approximate with if I take, if I take n sample, okay, what should I should have a yield the dimension of, okay, so how about this? Let me actually do this to match with our notion, right? Y observed is in Rn, capital N. This is better. Because then it's matched with what we have done. Then you don't have problem, right? This is N, capital N. Now I'm use only N samples. Monte Carlo with little n samples. If I do so, right, then this is approximately 1 over n, 2n summations of y observed minus AU RI, right? This is I from 1 to n time RI time y observed minus AU. Everybody okay with me on that? And notice, right? Notice this is a scalar. And this is also scalar, right? That is interesting, right? Because it's a number. Now, I'm gonna do one more step. I mean, this is just algebra. Everybody, just trust me. I'm gonna call P. I'm gonna call P as a projection vectors like we used before, right? I'm gonna define P as epsilon R1 transpose. I'm gonna make it a row vectors dot to Rn row vectors, right? If I call that and I can rewrite, this is equal. I'm sorry, this is the real equality. The only part that we do approximation is the laws of large numbers. Otherwise, this is equal to what? This is equal to 1 over 2n of, and this is interesting, y observed minus AU P transpose P y observed minus AU. Okay, so this in turn can be written as, nothing more than 1 over, actually I'm sorry, that must be 1 over square root of n here, right? And therefore we don't have n anymore here, I'm sorry, okay? And this is little n, not capital N, because of the Monte Carlo. Okay, so this becomes 1/2 of the norm of P of y observed minus AU square. So summary, what have we done doing? Very simple thing that we have been doing. It looks very silly that we did, right? We randomize and we do Monte Carlo approximations. So summary, we start from the misfit, which is equal 1/2 of the norm of y observed minus A times U square. And then we use laws of large numbers, right? Or Monte Carlo techniques. We approximate this with 1/2 of P of y observed minus AU. You see now, it looks like a projection, right? I've just, the only difference between the original, this is the original, this is the original, right? And this is approximations. And our approximations is the only different with approximation with the original one is just by projections, right? And you see, remember that I start with random projection. I just suddenly introduce the matrix, right? P, remember up here, on the way up here, I introduce the matrix. But you see, what we in practice, I don't need to introduce. It's just it's a naturally come out. In other words, we also have derived the random projection framework using just simply large numbers. Everybody see that? We should derive it, right? So let me call this misfit. Let me call, right? J. Remember, there's J is equal to the misfits plus the revelization term, and I will call J tutor is 1/2 of P of 0 minus AU plus alpha over 2 U minus U0. So they are, the only difference is now I have projection, but we have to derive it, right? Questions, right? Questions. So of course, right? You and let's also U. Let's also 1 second, please. Let me call U star is equal to admin. To take minimization of J, you got U star, and I'm gonna call U star N, which is our approximation is admin. The minimum, you take the minimization of U tutor, right? Okay, question for us, and this is the final thing, right? How far, right? Can we, how far is it, right? Is J approximate J tutor approximate J? Is that true? Can somebody tell me? The first question is actually very clear based on what we learned. J tutor and J, and why? Can someone tell me? Remember, J tutor is a random projection, right, of the J, and we just prove, right? Thinking about this at the Z or X, right? Remember the P projection X, right? This is therefore it is clear. We're gonna go through it, right? This is clear, right? By Johnson, Linda Strauss, or Linden Strauss, or right, Linden Strauss, or the random projection that we did, right? I think that the second one is more difficult. I mean, the second one, what we care about, right? Why? We want to solve. What we care about is U star. We don't care about J. We can make mistake in the objective function, but we don't want to make too much mistake on the solution, right? Of the optimization or the inverse problem. Okay, so we're gonna answer each question. The first question is clear. One is clear. One is clear. As we know from random projection or Johnson, Linden Strauss, that J is not very far, right, away from. So J tutor is only 1 epsilon away from J, right? Because that's exactly projections. We know this is not very far away from the actual J, right? That is not far away from actually with high probability. With high probability. How high? We only characterize up there, right? Let's not go into the detail. Now for two is actually a little more difficult, right? And for the rest of the class, we're gonna go through 2, right? U star is UN star. How approximates? How is it? How far away? We need a couple of things, right? First, notice that U satisfied what equation? U star satisfy we take derivative, right, and set things equal to 0. And if you take derivative of j, satisfy dj du, right, equal to 0. And that turn into what? Turn into A, right? A transpose A plus alpha identity times U star is equal to A transpose Y observed plus U 0. Okay, so if you set the take derivative and set it is equal to 0, that's what you get. Okay, and also UN star. Now UN star satisfying dj tutor du equal to 0, right? And in particular, what you get is A transpose P A plus alpha I U star, and very similar A star P transpose P Y observed plus U 0. Okay. So we have two equations, right? One for UN and one for U and star. Okay. So let me call, right? Let me call this as B. This is original matrix, right? This is B times U star is equal to little b. Oh, let me do little f here, right? B U star equal to f. This gonna be tutor, right? And this is f tutor. So you see that the U star n is a solution of the perturb linear equations, right? Everybody see that? It's just a solution of the perturb equations. And therefore, right? Therefore, we can actually characterize. We can characterize the error. We can characterize the error between B and I'm sorry, between U star and U, right? So and this is a famous result in linear algebra, right? From linear algebra, we know from linear algebra. We know what? We know that the distance between UN star minus U star relatively to U star, and I ignore on the vector, right, is less than or is equal to the condition number of B over what? Over 1 minus condition number of B times delta B over B. I'm going to define what delta B in a second, right? Over B times delta B over B plus delta F over F. And this is linear algebra where delta B is equal to B minus B tutor, right? Delta F is equal to F minus F tutor, and kappa B is the condition number of B. Okay, so that's what remains, right? Remain is to estimate what remains. So let me box. Oh no, I should do that. And you see, this is beautiful, right? Because it's intersect with, you know, linear algebra, function analysis, and everything, right? Probability together in order for us to characterize the error in practice. Okay, so what remains estimate delta B over B, right? Because that's the only two player in delta F over F. And we already did that. So that's a nice thing because delta B and delta F, we already know. Okay, so we know, right? We know from, let me go up here, right? Let me go up here. Let me go up here in the corollary. Let me call corollary star, right? So we separate two things. So first, estimating element delta F first, right? Okay. Estimating delta F is easy. We're gonna use the delta F is equal to the F minus F tilde, right? And then by definition, we're gonna plug F and F tilde. You do subtractions, right? You do subtraction. What you have is A transpose, right? What you have is A transpose of P transpose P minus identity of Y observed. Okay. Okay, so that's the first terms. That's the you just do subtracting together, and that's what you get, right? So nothing more difficult than this. It's easy, and this, right? By linear algebra, we know less than is equal to A, which is the fixed matrix times P transpose P minus I, and Y observed. Everybody okay with me on that? Just inequality for matrices and better, right? But from corollary star, we know that P star P minus I less than is equal to epsilon with high probability. So I'm lazy to carry on a probability, right? I'm just say high probability. So you just simply carry the probability over. Then this is nothing less than is equal to A, right? Epsilon Y observed with high probability. Okay, so in other words, therefore delta F over F is less than O, right? Order epsilon with high probability, Okay, so now we need to next thing we need to estimate delta B, and same story. Estimating delta B, remember that delta B is equal to what? Is A transpose B transpose P A minus A transpose A, right? But this is nothing more than the norm of A transpose P minus identity A. Everybody see that? Easy, right? Okay, but then again, less than equal is a linear algebra. We know that is less than A square P transpose P minus A. I'm sorry. And this we know, right? By corollary star that P transpose P minus identity is less than epsilon with high probability. Okay, so this is less than epsilon a square, right, with high probability. So together, therefore, right? Therefore, we go back here, right? So everything is that okay? Actually, why don't we do this one more step? One more step, that is delta B over B is less than epsilon, right, with high probability. Okay, so this is what we got. One of them, let me call this 1, it is 2, and this is 1. Okay, let me call this 2, and let me call this 3 instead, right? And then 1 is what? This is 1. This is 1. And in fact, right, 1 you need one condition for 1, right? One condition for 1 that we have with, right, with B inverse. If the norm of B inverse times the delta B is less than 1, this is true. If without the condition, we don't know, right? Okay, and this by a consequence, right? Consequence, right? And this as a consequence, B inverse. We can choose, right? So that this is delta B less than or is equal to 1 with high probability. Right, by choosing epsilon small. So together, so we have this is 4. So we just combine all of them by union bound again, right? So that's the beauty by union bound. Okay, so we characterize every error. Everything is ready for us to write the final results for our error estimations, right? So from now 1, 2, 3, and 4. And the union bound and the union bound. We have that the error in the solution U star minus U star n, and this is the thing, right? Is order epsilon, right, with high probability. Okay, so any so far was on conclusions. In conclusion, right? In conclusions, we start from Y observed minus AU in N, capital N, right? Which solutions, which solution we don't know typically, which solution U star. We, by the laws of large numbers, right, or random projection, we use the laws of large number to derive random projections. We get to P, Y observed, minus AU, which is now Rn, a little n, I'm sorry. So n is less than capital N, we have huge data reduction, right? Huge reductions in the data. And yet, we know with this is solution, right? And with solutions, U star n. And we have shown that, okay, we can not only be able to reduce the dimensions of the data, and yet our solution can be controlled, right, with high probability. Okay, that's the key, right? Because we want the inverse solution to be controlled. Any questions? Ella, can you still hear me?
Yeah, we can hear you.
Okay, perfect. Okay, let me summarize of our lecture. Right, I know it's fast. I'm tired too. Let me do summary what we have done. Summary. You know, listening is even harder, right? I know that. Summary. We start with inverse problem. We start with the inverse problem in high dimensions. And notice that I just showed you the data reduction of projection, right? We can do for the parameter as well. Inverse problem in high dimensions. That's what we do. We started with, right? And then we randomize. We randomize it to get to inverse problem in low dimension. So by randomizations, we get to the inverse problem in low dimensions. And that's very nice, right? But what? I mean, if you get to low dimension and you get the very bad solution, and then so what, right? And the key is no, we still can get a very good solution by a concentration of measure, which concentrations of measure, right? We show that we show that no solution, this is solutions U star, and this is solutions U star n. By concentration of measure, we show that U star of n, U star minus U star of n is equal to 0 epsilon with high probability. Okay, in fact, we can also show, we actually prove a statistical Morozov discrepancy principle. We didn't do that in this class, and the proof is actually similar, that if U star is a Morozov satisfying, okay, is a Morozov discrepancy satisfying solutions, then then u star n is also a Morozov discrepancy satisfying solution. Okay, so we also this is also we can prove this, right? But we didn't we don't have time. Okay, so this is the end of our lectures. Any questions? We're gonna send this to you. Okay. And now I know it's tough to do in such a short time. But if you are interested, right, we can talk more about that. So we develop also unified theory, right? In terms that one of the methods that we just show you here is called randomized method, which is what we did. But we can use exactly the same randomization technique to cover many other methods, right, in a one unified framework, which is very nice. But we don't have time to cover it here. Any, let me see, chat, there are 2 messages here. Okay. Okay.
Can I have a question?
Yeah, please.
So does this method only work when you have the analytical solution? So you can write that as AU as a forward.
Yeah. Now that's a good question, right? Again, I choose the linear problem to show you the nice theory, right? The theory also goes through for nonlinear inverse problem where you cannot even write. Remember that we have a nonlinear problem where you have GU you don't know. You have to solve a discretized problem, right? And evaluate solution. The theory also go through for a sub-Gaussian process. And we have that paper. I can send you that paper if you send me an email. Yeah, in which of course you don't know the solution, you cannot write it down. But of course you have to assume something, right? Assume that some sub-Gaussian things. Very good question.
Okay, if there are no further questions, then thank you very much, Tan, for your time and for the well-explained talk. It was a very nice lecture.
Okay. Okay.